Hello everyone, this is Dr. Nimish Kumar Srivastava, and in today's video lecture we are going to discuss about the power penalties, that is power budgets. What are the terms associated with the power budget? So in this video we will discuss in details about all these peculiarities, and we will try to encapsulate those ideas in framing some formulas that could easily help us to directly calculate the power loss that is happening in a particular system, so that we can calculate the safer distance for a optical fiber, after which we can fit the repeaters. So in this we will first move into details about that power budgeting. So this is the figure for the power budgeting, very important figure related to power budgeting. In this we can easily see that we are having a transmitter and the receivers. This transmitter and receivers are connected by a channel which is called as an optical fiber. So whenever a source is emitting a photons, that means it is emitting optical signals. Those optical signals will be directly coupled into the fiber with the help of a fiber fly lead. This fiber fly lead is very important for achieving a good coupling with the fiber. And after this we are attaching this fiber fly lead basically connected with the connectors, and if we directly want to feed the optical signals into the fiber, then with the help of connector we directly attach the optical fiber with the fiber fly lead, and which is directly now get connected with the optical signal. Now apart from this, suppose that if we want to communicate between a transmitter and the receiver that are placed at a distance of around 500 kilometers or even 1000 kilometers, then for that in a single fiber, then for that it is not possible to draw the single fiber of having a 1500 kilometer length or 1000 kilometer or 500 kilometer length fiber. So for that we are having a fiber spool of some standard length. Suppose that if it is of 10 kilometer or 15 kilometers, then we require a separate fiber spools, and those fiber spools optical fiber, now they are going to be connected together with the help of a technique which is called as a splicing technique. So with the help of splicing technique, all those fibers will be internally joined so that they can lay down for a distance of around 500 kilometer or 1000 kilometer. So that why we are having this word LSP, that means related to the splices. Now this, after this, if you require to test the strength of the optical signals, or you want to monitor the what is the strength or even some other parameters related to the optical fiber, then you can do it directly by connecting a connector at that particular point, and that connectors will be directly connected with the test equipments. But this is required as per your needs. If you don't want, then remove that thing and you can directly connect the optical fiber with the help with the receiver. And on the receiver side also you are having one connectors which is internally connected with the photo detector. That photo detector going to directly respond as per the number of photons that is incidenting on that particular photo detector. So based upon that, it will convert that photons or optical signal into its equivalent electrical strength, and from there we can easily get our original signal back. So this is the entire process that is happening in calculating the power penalties or in calculating the power budgeting. So for this, what is happening? Apart from that, we can see that in the formulas. So this is the basic intermediate formulas that we have to keep in mind in order to form a concrete relationship which can be directly used to calculate the power budget or power penalties. So we have to first find out what is the channel loss, total channel losses that is occurring inside the fiber. So this is formed by a combination of alpha FC plus alpha J into L plus of alpha CR. Now the thing is that what is alpha J? Alpha J is basically your attenuation that is happening at the joints. Alpha J is the attenuation that is happening at the loss due to joints in dB per kilometer. Similarly, your FC is basically FC is related to the fiber coupling. and finally your L is the length of the fiber, and alpha CR is basically a fiber connect, basically a attenuation that is happening at the connectors, which is indicated by alpha CR, and alpha C is the fiber cable loss per kilometer. So this is the formula that will going to give us the total channel loss, and this is the formula that we have to incorporate in forming in concretizing your full formulas for the calculating of your power budget. So this is the numericals that can be framed just for asking the what are the joints loss, right? So in that case you have to use this formula for calculating that losses, that is less loss, that is especially for the channel means optical fiber. So in that channel we have seen that in that channel medium there are various joints, various connectors, various coupling, fiber coupling. So we have to include all those attenuations, and we can now directly calculate the total channel loss. So the question here that is been asked is to calculate the total channel loss. What are the terms that has been provided is the length of fiber is 4 km, attenuation cable, fiber cable attenuation of 5 dB, the splicing losses which is happening is 2 dB per kilometer, and the connector loss are 3.5 and 2.5 dB. So these are two connectors loss. So we have to put these values for the alpha CR. So alpha CR is 3.5 as well as 2.5 dB. Apart from that, alpha FC is also provided and alpha J is also provided. So we can directly put these values, multiply with the length, we will get the final channel loss or total channel loss that is occurring inside the optical fiber, because optical fiber is basically the channel. So you have to calculate all these things. So in this way also a short question of around 2 marks or even 2.5 marks can be asked in the semester or even in the STs. Now this is the formula that we have calculated by considering that there is no dispersion equalization. What if there is some dispersion? So if there is some dispersion, definitely because of that there will be some attenuation. So we have to incorporate those attenuation also. So that is something given by this formula, that is the total channel loss including the dispersion equalization penalty, which is given by CLD. Now this have to be included. That means your channel loss is now, which is earlier it was given by a expression CL, now we are naming it by CLD. When we are including the dispersion equalization, then we are just reframing the words and it is CLD, and we are also including the penalty, that is loss that is occurring because of the dispersion, that is DL. So this is the thing that one have to keep in his mind, because sometimes in what is happening in the examination, that examiner is asking the channel loss without considering the dispersion equalization, and in the another part they are going to ask that find the total channel loss if the dispersion equalization is so and so. So you have to keep this point in your mind, that you have to put this formula of put this expression of DL only when it is provided in the question, otherwise don't put it. So after this we have to calculate the final power penalty formula, so that we can directly use that formula to calculate the overall total losses that is happening inside the system, receiver system. Now the power budgeting of a system can be done by a formula expression Pi equals to P0 plus CL plus of MA. MA is the safety margin. Why we are using safety margin? Because whatever the instrument that you are using for establishing a optical communication link, that includes various instrument like sources, detectors, amplifiers, everything. So you have to keep in mind that these sources and as well as the detector are made up of some material, that band gap semiconductors. So these materials also deteriorate as the time progresses. So if you are using the same instrument after 4 to 5 years of its inclusion in the system, definitely there will be some noise, there will be some loss that it is going to add up in the system performance. So we have to keep that margin in our mind. We have to include that margin also, so that we can get the correct result for that. And that is something done by a safety margin given by a MA. So its value is generally 6 dB for LEDs as well as 8 dB for lasers. Although its value going to be provided in the numerical or in the question if it is asked in the exam, but for generalization or for just interest of the some points to be remembered by some some students or some engineers, they want to keep all these things in their mind. So for those, MA is basically generally 6 dB for the LED and 8 dB for the laser source. Now this, what is PI? PI is the mean input optical power. So this is mean input optical power launched into the fiber. Similarly, PO is the mean incident optical power required at the receiver. And CL, we have already discussed what is CL, what is CLD. CL is the channel loss without incorporating dispersion equalization. CLD is the channel loss incorporating the dispersion equalization. So after this, what is the total channel loss that will be given by? We have seen in the equation. So as per this, the equation 3 will be modified as P0, Pi is equal to P0 plus alpha FC plus alpha J L plus alpha CR plus of MA. In this we have not included the dispersion equalization. So if we are including dispersion equalization penalty, then we have also put the term DL, right? So we have to keep these two equation in our mind. As per the need, you have to put these values of DL, and if they are asked, put it. If they are not asked in the numerical in the question, don't put this value of DL. So now let us try to visualize all these terms with the help of one numerical. This numerical is directly taken from the book Senior. Author is Senior, Optical Communication. Now in this, what is happening? We are using a system, long haul single mode optical fiber system, that is operating at some wavelength given by a 1.5 micrometer, having a mean power launched from a laser transmitter, which is your PI, cabled fiber loss 0.4 dB, splicing loss 0.1 dB, connectors loss 1 dB each, as well as mean power required at the APD receiver, that is avalanche photodiode receiver, is minus 55 dBm for 35 Mbps when your receiver is receiving at a 35 Mbps of speed. Similarly, when it is operating at 400 Mbps, what is the power, mean power required? So this is your P0 and this is also your P0. And the final is safety margin, which is given by MA, already given in your question, right? So we are having fiber cable loss, which is known as alpha FC, and the splices loss. So we have to include all these things in the formula. And the thing is that the question is the maximum possible link length without repeaters when operating at 35 Mbps. So we have to consider this PO value for A, and it may be assumed that there is no dispersion equalization penalty, means that we have to discard the term DL. And now we can directly put the formula, that is your total channel loss, which is given by alpha FC plus of alpha CR into alpha FC plus alpha J multiplied with L plus of alpha CR plus of margin, safety margin. So we have to use that formula. So this is that formula. Pi is equal to P0 alpha Fc plus alpha J into L plus of alpha Cr plus of alpha Ma. So by using this, just put the values, and alpha Fc values as well as alpha J value is already provided to us. Put these value, you will directly get the value of the, what is the length of the optical fiber, maximum possible link length without repeaters. So that link length is 86 kilometer. Now this is happening at a rate of, when your receiver is at the receiving at a rate of 35 Mbps. Now what if we are increasing the rate of your APD, that is operating at 400 Mbps, speed is 400 Mbps. Now what is happening at this point? Let us try to visualize the thing. Now in this thing, again we have to put the same values in the same formulas. The only difference is in the PO. So your PO will be now minus of 44 dBm, and then we have to put the value of alpha Fc plus alpha J. This is alpha Fc and this is alpha J, which is coming out to be 0.5 dB. So that's why it is 0.5 dB. Now divide it 32 by 0.5, we will get 64 kilometer. Now the next question that is asked is about the reduction in the maximum possible link length without repeaters of part B when there is a dispersion equalization penalty of 1.5 dB. Now you will see what is happening if you are including a dispersion penalty. How it's going to affect the performance of the system, whether the maximum length of the optical fiber without using a repeater going to decrease or increase. So we will see it with the help of this formula, this values, and try to evaluate what is happening to the length of the fiber. So after filling all those given parameters, we will see that the length of the fiber is coming out to be 64 kilometer. So the conclusion is that the moment you are incorporating a dispersion equalization or dispersion equalization penalty in the calculation of the length, you will see that the length of the safest length for the optical fiber without using repeaters is decreased by a 3 kilometer, right? So dispersion is the main culprit that is responsible for this. If you are including dispersion, definitely it's going to put down your safest length of the optical fiber without the involvement of a repeaters. Now next thing is, once we have got the basic idea about all the types of losses that is happening inside the optical fibers related to joints, related to splicing losses, as well as related to the coupling loss, we have to now visualize what is happening inside the system. Like if we are performing a receiver, we have visualized the receiver by the power budgeting. We want to know what is the safest length of the optical fiber that could be deployed without the use of repeaters. Repeaters, we know that what is the purpose of repeaters. Repeaters is to regenerate the original signal back. So obviously we require a less number of repeaters for establishing our optical fiber link. So that is the main thing that we have to keep in mind, because the moment you are increasing the number of repeaters, definitely it's going to add on to the overall cost of the implementation of the optical system or optical link. So we have to keep this point in our mind. Various culprits are also there that's going to decrease that length of the optical fiber. That main culprit is the dispersion. So we have already discussed what is dispersion in our unit 2. So from here we have started with the basic phenomena, how those phenomena is deteriorating the performance of a system, and then what is the main role of the dispersion in decreasing the safest length of the optical fiber without the involvement of the repeaters. So this is all we have discussed in this lecture. We started with the basic diagram. This diagram we have visualized that how different parameters going to be incorporated in the systems. After its inclusion, we have to build that some formulas. So as there are channels involved, as there are connectors involved, as well as some the other phenomena like fiber coupling, as well as the dispersions are also involved. So by incorporating those things one by one, we have formed some solid formulas which can be directly used in order to calculate the power penalties. So we started with the alpha, we started with the CL, that is the channel loss, and the channel loss we formed this formula. Then after that we solved the numerical, then we have included the dispersion equalizations, got this formula. And I have already told you that include this formula only when it is required, when it is asked in the question. Otherwise just neglect this term DL, because we know that it's going to deteriorate the performance of the system. So if it is not asked, don't incorporate this thing, because otherwise there will be some difference in what you are getting and what actually a examiner want to see. Suppose that examiner want to see a length of the fiber to be 64 kilometer, but you have already included the dispersion equalization penalty as per your need, and you have degraded the overall length of the system. So that means there will be a variation in the length of the systems from 3 to 4 dB, from 3 to 4 kilometer. So that's not required. That's not any particular examiner is expecting. So in our next lecture video, we will try to visualize other important parameters related to this. We will try to visualize the intensity modulation with that detection, then coherent detections. What are those coherent detections? Subdivisions, that is homodyne and heterodyne. So we will see in our next video. Thank you all.